Hi.
Hello.
Oh, wait, it's not open. Oh, okay. Permissions. Okay, I will give you the slides for the course today in the chat here. It's not on Arduino yet. Okay, the slides are on Arduino actually. I don't know why it doesn't want to upload in the chat here. Okay. Can you all see the screen? I guess it should be good. Okay, we'll wait a few minutes and then we'll start. Okay, I think we will start. Just can you hear me?
Yes.
Okay, good. Okay, we will start. Okay. So I hope you had nice holidays, and I wish you all a very happy New Year. And yeah, and today will be the last course. So the last course where I teach you a lesson, and next course would be the exam, as stated in the email. So exam will be the same as the course for deep learning, with a short multiple answer tests. And I took into account all your remarks for the last one, so it will be less ambiguous. You will know when there are multiple answers or if there are only one. And yeah, again, this test will not be there to trick you, so don't worry. It's just to check that you listen to the course. And of course, there is next week. Remember the project, the little project presentations. So same format as the first part of the course for deep learning. And I know because there was less time than for deep learning to do the projects, because I also know that you had holidays and maybe you had other things to do. I can imagine. So today there will be no TP, but it will be a free session where I can help you on your projects if you need. If you have any question, be it coding or be it just question of something doesn't work or you don't know what to do, you're stuck at some place. So I'm here to help you on this. And next week we'll have the small presentations, and you will hand in your reports on those projects. And that will be the end of the course. So okay. So today we will talk about what is called model-based reinforcement learning. Until now, in all the courses, we only saw and only talked about model-free reinforcement learning, because at no point we assumed that we knew something about the environment, especially about the reward and the transfer function, except remember in the first course where we did dynamic programming. In dynamic programming, you have full access to the environment, so you can compute exact algorithm like policy iteration, value iteration. But in this case, it is not. We are not even approximating. So, but it is not considered technically model-based reinforcement learning. Okay. So first, a recap of the reinforcement learning problem, and then we will see what is planning. So planning is defined as any computational process that uses a model to create or improve a policy. So the definition is very broad, but planning basically is any process that will, at inference time, choose a sequence of action that it finds optimal. And planning does not necessarily involve learning. But planning can be a purely heuristic, or can be a mixture of learning and like components that were learned and components that are like hard-coded. In traditional robotics, planning is usually doesn't involve any learning, even though now we see a paradigm shift towards incorporating even more learning inside. And when you have a model, so the model is usually something either that you hard code or that you learn, model of your environments. And it describes the transition function of your environment, and you want to use it for planning, because then if you have the model of the environment, you know what happens when you take any steps in the future, so you can anticipate and explore in advance multiple paths. And that's what planning is about. Using the model, you want to do planning to have a good policy. So that's the typical reinforcement learning loop we have. And basically, in model-based reinforcement learning, you want to replace the environment that you have access to with the model. So in a way, you want to actually approximate and learn the environment so that you don't need anymore, in theory, to interact and with the environment. You don't need anymore to take samples in the environment of experience to plan ahead and gather experience. Because if you learn the transition function that gives you the next state st+1 given st and at, and if you learn the reward function that gives you the reward you receive at every step, then it completely describes your environment. So the model is anything the agent can use to predict how the environment will respond to its action. So concretely, as I said, the transition function or the reward function. And model-based reinforcement learning involves learning, and especially learning the model. And how we will learn the model, we will still use experience tuples. So we will still be sampling. So you can imagine some policy at some point that is good or bad, or maybe not finished training, or even maybe random, that acts in an environment, and this policy gather experience, same as in Q-learning, for example. And this gathered experience will be used, these tuples will be used to train the model in a supervised way. So because, for example, in these tuples of experience you have gathered, you know that you were in state A and took action S, and from experience, you know that you arrived in state S prime. So you can train a supervised model to predict that. Same thing for the reward. And the model learning basically involved predicting R and S prime from S and A usually. The model can be anything, can be Gaussian process, random forest, deep neural network, linear function. Usually, and today, those models are mainly composed of deep neural networks, especially because we talk here about deep reinforcement learning, but also because they are the ones who work the best, especially when you have high dimensional states such as images. And we will see that later in the course. Another way of seeing the reinforcement learning objective is this view. So it's the same loop as you just saw before, where S here might be, for example, an image. So the state that the environment gives you at every stage is an image. And that's why you need, for example, for the policy, as you saw in the previous course, you might need to implement the policy with a deep neural network that takes as input the image. And so the first layer will be convolutional layers, then maybe dense layers in the neural network, and then at the end you output an action directly. So for example, for policy gradient method, that PPO, you would implement the policy like this. For deep Q-learning, you don't implement the policy, but you implement the Q value in this way. And you don't output actions, you output action state values, and then you choose the action corresponding to the maximum value. The idea also in reinforcement learning, remember, is the Markov property, which allows us to factorize the joint distribution of the whole trajectory. So you have the trajectory starting at S1, take action 1, go to S2, etc., until you arrive at ST. So this is whole trajectory. And you can decompose the probability, the joint distribution, joint probability of this trajectory thanks to the Markov property, like this on the right. And the main objective is to maximize the total reward. Potentially, here there is no discount factor, but also you can imagine you can have a gamma factor in the sum that is weighted. Here it's just equal to 1. In model 3, we assume this part is a known and we don't even attempt to learn it. So remember the transition function. In model 3 learning, we assume nothing about the environment. We just know it's Markov. It has Markov property, and that's it. And still, we have good algorithms that learn good policies given enough interactions. Well, in model-based learning, it's quite the same. We assume this is unknown. I mean, there's two possibilities. Either we know it and so we already have the model, we are hard-coded, or it is unknown and we want to learn it. Here, remember, with all our previous courses in model 3 reinforcement learning, all the different algorithms can be described like this. With a given policy during training, you generate samples. So you interact with the environments, and then you take this experience that you just generated by interaction, and you want to fit some model. So here the model is not the model as in model-based, but just your function, you mean, that you want to approximate. So you can have Monte Carlo policy gradients to estimate the return, and then you improve the policy with the policy gradient, for example. Or you can do as in Q-learning or in actor critique, you can also fit a Q function. And then using this Q function, you can find the best policy by taking the greedy policy with respect to the Q function you just learned. So here, you don't directly learn the policy anymore, but you first learn a proxy model, which is the Q value we saw. And then remember, you take the greedy policy with respect to this Q value, which improves your policy. A third way, and that we will see today, is in model-based, and you want to learn a model of the environment, for example, estimate the transition function, probability of the next state given the state and action. And using that model that you learned, you want to optimize the policy. But this time, you will not have to use policy gradients or Q values necessarily, although you still can mix them. So to summarize, model 3 reinforcement learning, we ignore the model. We just perform sampling and simulation to estimate rewards, meaning you don't assume anything, you just interact, and by interaction and design of the algorithm, you actually can improve your policy at every step. In model-based, we want to calculate the optimal actions to take using the model directly. And the idea is quite similar. I mean, it's not similar, but it reminds us of the dynamic programming where we had access to the whole model. So technically, by seeing the whole model intuitively, for example, remember the mini-grid example, you could imagine the shortest path quite directly. You could visualize it and find it pretty easily at inference, just by looking at the grid and say, okay, so if I go in that direction, I can arrive at my targets quite easily. And in model-based reinforcement learning, we want to use the model to perform planning, which is calculating those optimal actions sequentially using the model. So remember, Markov decision process is defined by set of states, action, a transition function, reward function, and then you have a start state, discount factor potentially, and potentially horizon. In model-based, you assume that you have the set of state and actions, and for example the reward function, and you want to learn the transition function and potentially the policy. So if you only do model learning, you just want to learn the model, well, you just learn P of S prime. But usually when you do model-based reinforcement learning, you also want to find a good policy. You just don't do model learning alone, and so you want to find also the policy. So in many examples of models, actually in many games like Go chess, like board games or stuff like that, the model does not need to be learned because the model is exactly defined by the rules of the games. Meaning, for example, in chess, it is not super difficult to code the rules of chess, for example, because you can define for every piece if they are allowed to move or not, and what can they take, and also encode all the positions of the boards of the piece on the board. So in chess, if you know the rules and you see the board, you know everything about the environment, and you are not only in a Markov state, but also you can actually plan in your head what would happen if you would make those moves, and that's the whole purpose. That's the whole. I would say that's the core thing in the game that allows human players to plan ahead, multiple moves ahead, or same for Go. While you have the best grandmasters who can actually anticipate moves and plan ahead in their head up to 15, 20 or more or 50 moves. And you want to use this opportunity to plan ahead. But in other cases, the model that you want to learn, and maybe you don't have access to it, would be, for example, the physical laws, the dynamics of the world. So in a robotics environment, for example, well, the model is way more complicated because it requires understanding the interaction of objects between each other, contact interactions, gravity, what would happen, for example, if you put a cube on top of another, would it fall, in which condition would it fall, stuff like that. So here the model is exponentially more complex to simulate. Oh, sorry. To simulate, but you can still try to learn. But we don't have access to it anymore. It's not as simple as the rules of the game anymore. You could ask the question why we want model-based. Why not just settle for model-free, which is arguably simpler to implement? And the question is, the answer is sample efficiency. What is sample efficiency? It's the metric that tells you how much interactions with the environment you need to actually arrive at a good policy at the end of training. So this quantity is almost never known in advance. You cannot really compute it. It's not a precise number, but it's more like a order of magnitude, and usually you find it by experience, by having experience in the field, and you try multiple environments and you start to understand usually the order of magnitude of interaction you need to actually arrive at a good policy. And there is a interesting property of this quantity is that the sample efficiency of different algorithms is not the same, and more than that, you can actually rank them based on their sample efficiency. In particular, so model-free reinforcement learning is known to be less sample efficient than model-based reinforcement learning. And why is that? well, the intuition is actually quite easy to see. In model 3, we don't assume anything about the environment. We don't put additional knowledge. We don't put additional rules, or we don't try to learn the rules of the environment, of the game. We don't try to learn the physics. We just try to learn directly a policy or a Q function. And that's why you can imagine you need way more interactions to find a good policy, because it's as if you are trying to learn a policy while not knowing all the rules of the game. On the opposite, model-based, especially, for example, in an environment like games where you know the rules and are exactly coded, then it's much more sample efficient, because much of the information is already provided to the environment, and he only needs to find a good policy, and he can use planning to its advantage. Planning is really effective when you have an existing model to learn a good policy really fast. Also, on policy and off policy algorithm have different sample efficiency. We talked about this also already. Off policy is more sample efficient, because remember, off policy means you are not fitting the policy or the Q function using the data of the current policy. So it allows you to use any data and potentially reuse data from the past. And because in off policy, usually you will want to reuse data as much as possible. So with the replay buffer in Q-learning, for example, because you reuse data, then the learning is much more efficient, in the same way as in computer vision, you do multiple epochs to converge. You just don't only do one pass over the whole data set, you do multiple passes. On the other hand, with on policy, you can only or at least in theory, you can only reuse the data once. Once you collected it with the policy, you can use it right away. But then later on, when the policy got better, you cannot use that old data anymore, because it has become off policy, and the algorithm is not suited for that. So on policy is less sample efficient. And at the whole extreme, you have evolutionary algorithm. So that don't use gradient learning, but that you might have heard of them. For example, you have a population of agents, and you mutate them, and then you select the best N, the best K agents according to some fitness criteria. So it's like survival of the fittest, and then you generate again a new generation of mutants from those top agents, and again for a lot of generations, and at the end you end up with good policies without any gradient learning. But this takes way more interaction with an environment. Second reason is transferability and generality or generalization. Meaning we want to use the model for multiple tasks, and that's easy to see why. In a given environment, for example, in the case of robotics, or even just autonomous driving, the environments would most of the time be the same. For autonomous driving, no matter what the task is, meaning like no matter if you need to drive to location A or location B, which are two different tasks, the environment, the physics of the world didn't change for both tasks. So the transition function is the same, and so the model is the same. So the advantage of model-based is that if you learn a good model of the environment, then you can reuse it for different tasks in the same environment. For robotics, it would mean, for example, if you learn a good model of a robot that interacts and learn to do some task in a house, for example, then you can pretty easily define a good policy or learn a good policy using this model for a new task in the house, because the model is already quite good. So for the formulation of model-based, consider MDP with set of state S and action A, and you have the transition function. So remember, the goal of reinforcement learning is to select the actions to maximize the expectations of rewards. You already know that. And we want to learn an approximate model. Usually we won't have an exact model except for board games, for example, as I explained. You want an approximate model parameterized by some parameters. So this is already hinting that we are going to use deep neural networks, as you can see. And we want to approximate this unknown transition function of the underlying system dynamics. And for example, the parameters can be learned to maximize the log likelihood of observed data. So we have some data that was gathered from experience, and we have some sample. This is the observed data, and we can train the model, which can be deep neural networks, by maximum log likelihood. So this is equivalent to some standard supervised learning and regression problem. And then once you learn the model, you want to do the learn model prediction to learn a policy or perform online planning to select optimal actions. Those are different. Learning a policy is the same as what we did, meaning at the beginning we have a bad policy, which is we have a bad function that gives, for example, random actions to every state, and we want to learn. We want to learn the parameters, the weights of this policy, so that it improves, and at the end it gives good actions. And we will use the model to do that. Online planning is different because online planning does not involve necessarily any learning, and it only means it's only at inference time. Online planning means, for example, with heuristics. So if you have a good model, you can estimate what would be the future states if you take action B or action C, and then you can actually see ahead what would happen for every possible action you take, and you would choose the best action accordingly already by not predicting the future, but seeing foreseeing the consequence of your actions. And that's what online planning is about. It's not about learning a policy that becomes better, but it's about, at inference time, trying different, for example, possibilities and choosing the best one. Mathematically, our model will predict the next state usually. So you have a function that takes the previous state and the action you just did, and it approximates the next states. So you can define these models, for example, with rules or equations. In particular, for example, in the case of a purely physical system, like I don't know, some very simple pendulum in physics, or some or even fluid mechanics or stuff like that, you can actually write down the exact equations of the movements of the system. And so you don't need any learning, because the model then is literally the physics of the system. But most of the time, except if you are working on a very specific physics system where you can actually write down the equations of the system in time, usually the system is way too complicated to write all the equations, especially even for a simple setting like a robot taking a cube. There is way too many degrees of freedom, and the equation of the system, especially when you have contact between objects, is not super simple to write down. So you won't have rules or equations. And rules can also be the rules of the board game, remember. Second thing is we can model it, and that's what we will see here. So using Gaussian process, Gaussian mixture models, that's more like old methods, but can still be relevant in some cases, or usually deep networks. And to fit these models, we can run a controller or a policy that was trained, not only a controller. So controller is especially in robotics or in optimal control. It just means a controller is a function that that will give you action given a state. It's another word for policy, but it's broader than reinforcement learning. And usually a controller is hand-tuned and is hard-coded. It's not usually not a neural network or anything, and it's not something you run. But yeah, you run a policy or a controller to collect samples, trajectories, and this controller or policy is not necessarily the best, but can be also already trained. And then you, using this experience you gathered, you train the model with supervised learning, as I explained. And given the model that we learn, there are then two possibilities to learn to learn a policy or to have the best actions, and that's what I explained already. You can either do learn a policy, which will be model-based reinforcement learning, or you can do online planning, and which will be called model-based control. So in model-based control, given initial states, you want to estimate the action sequence to reach a desired goal or maximal reward by unrolling the model forward in time. So imagine that now you learn your model. In model-based control, the objective is to find the sequence of actions that reach the goal. And usually, this will not involve learning a policy, but doing some online planning. So in model-based control, we want either to find the sequence of action that makes us reach the final state as star. So at time t, we want to be the closest as possible to our end goal. So for example, in locomotion tasks, or like, for example, autonomous driving or drone flying, or even robotics, where you have some cube or some object you want to grasp. Well, there is a goal you have to reach. And so in model-based control, you want to find a sequence of action that reach your goal. Other possibility that is more general, you just want to find the best actions that maximize the reward. And usually reward are still somehow defined with respect to distance between objects. So usually in robotics, for example, the reward would be distance between your arm and the object to grab. So the idea of final distance is in the end it's quite the same objective. And in the first case, you don't need a reward for planning, but you don't need a reward model, especially for planning. You only need a transition model, so you need to be able to predict the next state. In the second case, because you don't have a specific goal, but you just want to maximize reward, you also need to be able to predict what is the reward for every state. So your model, f of theta, will now have to predict both state and reward. So given you have an initial action sequence, you unrolled the model forward in time. So you start at S1 and you have a list of actions, N1, N2, N3. You just you give them to your model, and you repeatedly apply the model to predict what would be the next state you arrive in given this sequence of actions. Then you compare and compute the error against the desired final state. So did I arrive to the state I wanted to go to? This gives you an error, and or you can compute the sum of rewards also, depending on your objective. And then this will give you some error function, and you can backpropagate the error function to the action sequence. through the model with gradient descent. So the question is, does it work? It does work, but there are multiple problems with this first simple approach. You can already see one, tiny errors will accumulate fast along the trajectory, meaning if on this diagram at every step the new state that we're in is not quite exact, but there is some approximation error, which there will be because usually we use deep neural networks. While these errors might accumulate, and at the end you might end up far off your objective, even though you are only making small mistakes at every step. But if you do a lot of steps, you might be really wrong at the end. Also, the search space can be too big for any policy. So it's not, this model will not give you a way to find the policy, and so you are still, if the space of different policies is too big, you are still stuck with the problem of finding a good policy in the beginning, because you don't have a good way for now to generate good actions in the beginning, and just guessing random actions sometimes is not tractable. Because with this model, with this algorithm, you might say, okay, so first we start with random actions, and then because we backpropagate the errors, we will correct the actions gradually. But if the action space is huge, it might not work. Also, another problem is if the model is not perfect, especially if it was trained on a precise distribution, it may have never seen some states, or particular transitions. For example, if the model was, in the case of robotics, if you train some model to predict from images, for example, to predict, if you train the model using data from interaction with some, I don't know, with some grasping some fruits on the table, okay, and then once you have trained the model, you want to resolve a task of grasping a water bottle. The model might not understand the physics, or just might not know how the water bottle would behave when trying to grasp it. And so we may land in those areas with those actions, and the model might be really wrong then, because we didn't train in on it. So this is an illustration. Because we have the errors that accumulate, we might arrive at some point where the model was not fit here and is really wrong. So first solution to this is, instead, so given your sequence of action, instead of unrolling the whole sequence of action and then backpropagating the error at the end, you execute only the first action of your sequence, and then you unroll the model forward in time, and then you compute the error to avoid propagating the error too much. This is called model predictive control. So we saw model predictive control. The other thing was model-based reinforcement learning. And so here it didn't involve any learning of a policy, because we assumed we had access to a controller that gives us actions. Here, we want to learn both model and also the policy, the same way we learn policy in reinforcement learning that we saw. And so the idea will be to alternate learning the two. So for example, first naive algorithm. So you see on the diagram that you have, so look at the black arrows, you have some policy that is defined and that is maybe trained, maybe during training, so not perfect. And this policy will give you an action given a state. And then you feed both the action that was provided by the policy and the states. You give this to the transition model, to your model that you learned, and the model will output you the reward and also the next states on the right. And you do that at every step. So in this case, you don't even need to interact with the environment anymore. And so the objective of this algorithm and the different steps is first, you run some base policy. So at the beginning of training, it will be, for example, a random policy, and you collect some data. Then you used supervised learning, as we saw, to learn the model. So you minimize, for example, the mean squared error between a prediction of next states and actual next states that you saw during in the data you collected. And then in the third step, you backpropagate this error through the model back inside the policy. Especially if the policy is implemented with the deep neural networks, you can do that. So, for example, remember in deep learning, when we had autoencoders, you can backpropagate the error from a decoder to the encoder through both networks. If you don't, in deep learning, implement some stop gradient or anything, the error will backpropagate as deep as it can go. So in this case, if both policy and model are implemented with the deep neural network, well, the error will backpropagate through both of them. And this way, and if we defined our error in the step 3 to be the reward or like negative reward, so we want to maximize the reward or minimize our negative reward, then this is a loss function, and we can update the weight of the policy function using the gradients that comes from the model above. Does it work? It does also better, and it is similar to what is called system identification in classical robotics. I won't talk about that because it's a bit out of subject, but it works pretty well. But still, we need to be careful, and especially the base policy. Sometimes a random policy is not enough and will not produce varied enough samples to learn. So you can imagine, for example, if you are especially in a robotic setting or like autonomous driving or like basically the real world 3D environment with physics, a random policy will do almost nothing interesting. A random policy will just move in circle or like do like very little interesting actions. Like there is very little probability that a robot arm will actually grab something and stack this object on a new object if you just ask for random actions. There is almost zero probability. So if you just use the data from a random policy to fit the model at the beginning, then you will very likely overfit to some very small portion of the state space and action space. And so that's why you need to be careful about the initial policy. But this method is particularly effective if we can hand engineer a dynamics representation using our knowledge of physics and fix just a few parameters. So that's what I explained. You can, if you know that the system is physical and you can write down some equations, and that, for example, there is too much equations to all write them, but maybe some of them are simpler and you can still hard code them. Then you just need to learn some very, very little parameters, and you don't need to learn a whole deep neural network. And in this case, this works really well. And there are multiple applications of this where you just basically fit a linear model on top of some physics equations or like dynamic system equations, and it works really well in robotics. But there is still the problem of distribution mismatch, as I explained. If, for example, at the beginning you have a random policy in red that collects data randomly, the model will be fit on these parts, and so the model from what it sees in the red region, the model can deduce, okay, imagine that the mountain, as you see, the altitude is the reward. You want to go as high as possible, okay? So from the rate data only, the model will naturally deduce, okay, so apparently the higher am I, the higher the reward. So then the gradients, when you learn the policy, the gradients will tell the policy, okay, improve yourself so that you get higher and higher. Here in the red region means going right. So the policy will learn to go right, and so on and so on. But then if you unroll this policy for like a long time, so if you just if you try this policy that you just learned with the red data, and you say, okay, now perform like 1,000 actions in the future, not just 10. Well, then the policy from the data she saw going right gets you higher all the time. So she will do that, and she might fall off the cliff because the model never saw that at some point you might fall off the cliff if you go too right. And this is what's called the distribution mismatch. And there is a particular problem that arises when we use deep neural networks with model-based reinforcement learning. Especially deep neural networks, they have way more parameters and are way more expressive than, let's say, Gaussian mixture models or like linear models. So meaning they can approximate way more complex functions, but they are prone to overfitting, especially if you don't have a lot of data. And so this distribution mismatch problem will get much bigger. So the question is, can we solve this problem? And do we need to collect data from the region that is known that after the cliff? And we can actually slightly do better. So you have version 1 of the algorithm, which is running the base policy, the random policy, and you collect random tuples. Then you do the same, you learn the model to minimize the squared mean squared error, so as we saw, and you backpropagate for example, the reward error into policy to optimize the policy. And then you add a fourth step where you run the policy, the new policy again, and you have new states and action into the ripple buffer. And now you can say, okay, now that we have a new experience that is collected, we can actually improve the model. Because if you learn the policy with only the rate data, and then you unroll the policy, and the policy is the new yellow line. Well, now you can use the whole yellow line to improve your model, because now you actually have data of what happens if you go too far right. And so now you can use the whole yellow line to learn the model again. And the idea is basically do a loop. Now, instead of only doing it once, so 1, 2, 3, 4, when you arrive at 4, you loop back to 2, and then you introduce some loop, and you alternate between the two. What if we make like a mistake, for example? So in this case, well, you can also reintroduce some replanning to correct model error. So this version is combining V1 and the solution we saw to avoid accumulating errors. So it's a mixture of both worlds. So same, you have a random policy, you learn a first model from this random policy, then you learn the policy to choose action, sub 3, and then you also use the trick that was used to mitigate propagating errors, and you execute and you plan some actions in the future, and you execute only the first plan action, so which gives you a new state S prime, and then you will happen this new tuple to do the sets and loop again. And this is called also model predictive control. And there are multiple ways of choosing action here. You don't have to have a policy. Especially you can do some online planning, for example. So you can, for example, sample action sequence from some distribution, or you can run actions through a model to predict future states, or you can choose action that leads to best outcomes. So far we have multiple versions. We had version 0, where you just collect random samples, you train the dynamics, and in third step you plan. You do at inference time, choose the best actions by comparing, for example, different paths. So I won't talk about planning on this course because this is beyond the scope. But you can use, for example, any planning algorithm from traditional robotics. The pros is that it's simple. There is no iterative procedure. It's just collect, train, and plan, and that's it. But there is the big distribution mismatch problem because you only did it once. So potentially the random samples did not cover a big part of the environment. The V1, you introduce the loop. So you did this, but iteratively. You collect more data and refit the model every time with better and better data. So it solves the distribution match, but you might still make mistakes if you have an imperfect model, and errors can accumulate. So the version 2, you replace the policy with that we just saw. The last slide, you replace the policy learning by model predictive control, meaning you don't learn a policy, but you collect the data using model predictive control. So at every step you replan, and the advantage is that it is robust to small model errors now, but it is computationally expensive because planning is computationally expensive, especially if the action space is big. But you have a planning algorithm at least. And then you have two ways of optimizing a policy. Either you backprop so for example, the negative reward through the model into policy, or you can do also sampling-based optimization. You can also choose to just maximize the policy with some model-free, some model-free way. And today, like nowadays, some methods, they blur the line even more between model-based and model-free algorithm because they might learn a model of the environment. For example, in ways I described in this course, but then they might learn the policy without using the model. Like they might learn the policy with Q-learning, for example. And the model was actually learned to better shape the representation of the inner layers of the value network or the policy network. So now the lines between model-based and model-free reinforcement learning are even more blurred. An example of a successful model-based algorithm and how it might be implemented in practice. So there's this algorithm called Simple from Google Brain, and they applied this to the Atari video games, the same games you saw in the practical session. And So it's an entirely model-based deep RL algorithm based on video prediction, and it achieves competitive results on Atari games. Good thing is that it outperforms all model free algorithm. So now it's outdated because there was an even better one, but we will stick to this algorithm for the course. And also, so it outperforms in terms of learning speed, especially. So in terms of sample efficiency, it needs way less samples than model free algorithm to converge. Usually on Atari, if you want to have a really good performance on all games, the numbers is around 200 million iterations. And here, Simple is able to have competitive results in only 100,000 iterations. So 2,000 less samples, which is 3 orders of magnitude. It's quite nice. And that's what we want to go toward, because reinforcement learning is still very sample inefficient. We need still thousands or millions of iterations, and ideally we want to go in a world where you only need tens of iterations or hundreds, as humans do. So the main loop looks like this, where you alternate between 3 main steps. You have observation, so data you collected. Then using this data you collected, you do the world model training. So it's just the model that predicts future states, for example. Here, in this case, they predict future images. So they have a convolutional architecture that reconstructs new images with like an autoencoder given the previous image. Now that they learn the world model, they can train the agent in the world model. So with the way I described, for example, you have the policy that gives a sequence of action, and you see the consequence of your action directly using the model. You don't need to interact with the environment anymore, because you have the model that mimics the environment by predicting the next frames, the next images of the video game. And then you backpropagate the error, and you have a better policy, and you can evaluate the agent in the real environment and collect new data using this new improved policy. And then you loop again. So visually, it looks like this. You have agent evaluation in the real world, in the video game, interaction, and you use this observation for self-supervised or supervised training, depends. The definition depends on how you view model learning. And then you use the world model to train the new policy. So this is the pseudocode. It's the same as what I described again, so it's a bit repetitive. And the results are quite impressive, because here you can see on the left you have a comparison with the rainbow algorithm, which is Q-learning, deep Q-learning that is improved and with a lot of implementation tricks. So it's a really strong baseline. On the right, it's PPO, so policy gradient method also that was tried in Atari. And the red line is the number of steps, so 100,000 steps that they train Simple, and the blue bars are the steps it took, either a deep Q-learning or PPO, to reach the same performance. So you see in most games, it took way more samples than Simple to converge. So the sample efficiency was greatly improved. But this method has its limits, and that's why it's a bit also it's a bit old now and not used anymore. Atari images are pretty simple. They are like they have like something like 84 pixels by 84, which is small, and you can represent all the information with such a small image. But real world images are way more complicated and have way more pixels, especially if you want to see interesting tiny details. And the dimensionality explodes. And there is also a lot of redundancy. For example, in the 3 images of the robots, all 3 images look quite the same, but still there is something happening. It's just that the changes are way more subtle. Like a small movement of the cube might actually might mean a completely different state, especially if you compare the photo where the cube is above or behind and the photo is on the left. Arguably, you could say it's quite similar, but the state is completely different. There is also the problem of partial observability, meaning, for example, if you see in those photos, it's hard to guess without the second image if the cube is behind or above. We don't have depth information, so we lack information, and also you don't know also the speed of the robot and etc. So this is problematic, and to solve this problem, you want to decorrelate learning the visual world and learning the dynamics, and that's what a lot of new methods try to do, is to you separately learn the distribution of images, the model of images, so reconstruct, and the transition function, and you will learn the transition function in the latent states. So remember autoencoder, you have it in the middle, like a hidden in the middle of the hidden layers, you have a small latent space of dimension that you choose that is way smaller than the initial image, and you can define the features like that are produced by inputting the image to the networks. You end up with the small dimensional features, and you can say that those features are the state S that corresponds to the observation O, and then you will learn the transition function in the state space S and not in the image space. So the advantage is that now the dimension is much smaller, and it's much faster to learn in a small space. So now you have 3 models. Usually you learn the observation model, so predicting the image, the whole image, so usually a convolutional network given a latent state. So you have some vector that lives in your latent space, and you want to reconstruct the image from it. So usually this is done by training an autoencoder, so that first maps the image to the vector and then back to the reconstructed image. You have then your dynamics model that takes a vector state that is your latent space and gives you the next one. So the advantage is now that this is fast, and you have the real model also that lives in the latent space. And so you can train by so in the case of a fully observed model, where you state ST and etc. were like simple, you would just first line you would just maximize the log likelihood of the model. Now we decorrelate the two and we separate the two, so we maximize in the latent space the likelihood of the transition dynamics model, and also we maximize the likelihood of the observation model. And the expectation is with respect to the transition model in the latent space. A lot of state-of-the-art methods use this principle and are really efficient now. This idea of learning a world model and learning this world model in latent space and not in image space. But then, so the algorithm becomes like this. You have a base policy, random or exploratory policy. You collect some data, Then you learn the latent embeddings, the latent features, latent states of observations using, for example, autoencoders, as I explained, and you learn the dynamics model. So this is the same way as before, supervised learning. You predict the next latent state given the previous one and the action. And then you use the model to optimize the policy. But then you might ask the question, how do you define the reward for optimizing the policy? And a way to do it when you work in latent space is doing the following, and it's an idea that is done a lot, is that you decompose the reward by a reward that takes just an action plus the distance between your observation and your goal observation. And that will be your reward signal. Finally, some challenges in model-based reinforcement learning that are still completely not unsolved, and so there's a lot of research. There's a challenge of under-modeling. It's especially hard to model complex dynamics, like contact dynamics. It's really not smooth. It's really not continuous. Just using deep neural networks on images might not work super great to predict, to build an accurate model. Sometimes in robotics, you have overfitting. Especially if you have deep neural networks, the model will overfit in the beginning of training when you have not a lot of samples, or like samples that are centered around a start state, especially if you have a random policy at the beginning. And then you might have difficulty difficulty with keeping training it if it overfit at the beginning. You have error compounds, as I explained. The big errors, small errors become big when you override the model for some time. And there is something I didn't talk about, but that is quite important: the notion of stochasticity of the environment and randomness. And sometimes the model is inaccurate, not because of like under modeling or overfitting, but because you cannot actually predict. And the thing is that with just a simple neural networks, the deep neural networks has no way of differentiating what is hard to learn from what is impossible to learn. Example, if you have an environment, just a video game, as I gave this example before. If you have an environment with in a video game where you have a TV in the background, and if the TV like broadcast, like, I don't know, random noise for some reason, for example, or if you just have some random component in your environment where something visually or just something happened completely randomly, you cannot predict, then the model will still try to learn that, but he actually cannot. And so it's not trivial how you can handle these parts. And we need to derive some ways of handling the stochasticity in the environment. There is some standard ways that you can imagine already. If you remember the course of deep learning, remember there was the variational autoencoder, where you do variational inference in latent space and you sample in latent space. Well, this is one of ways to do it. But there are other ways, and it's not completely perfect. Last thing is related to stochasticity, it's uncertainty, especially outside of the training data. This is a problem, especially with deep neural networks, because deep neural networks, they don't know what they don't know. They have no. If you train them on a specific distribution, when you test samples that are like out of distribution, they might give you completely bogus answers, but they are still very certain of themselves, and they have no way of telling you, oh, I actually have no clue. They will still provide you some answer. For example, in the case of classification, if you train them to predict cats or dogs and then you show them a car, they will give you some answer. They will not tell you, I cannot decide. They have no way. And it's a really open question of how do we teach deep neural networks to represent uncertainty and undecidability. Like we need a way for them to tell us when they actually cannot take a decision because it's impossible and not because just they made an error. Okay. So to summarize the two approaches, we had seen before model 3, which makes very little assumption about the model beyond the reward function but you don't even see the function, you just receive the rewards. The pros is that it's very effective for running complex policies, and it is the same usually in even way beyond reinforcement learning or machine learning in life. Like when you make little assumption about something and you let the system or the person or something like just optimize the final objective with enough interactions, it might discover the best way to do it. And on the other hand, if you give too much information, if you guide too much the model, so as in model-based, you provide more information, well, you might bias the model in some less efficient region of the possibilities, and it might not discover something because now it's biased. The cons of model 3 is that, of course, it requires a lot of experience, as you could maybe saw during your project and the TP. And it's also not directly transferable across tasks. When you train a policy on a specific task, the policy is trained for this task and this task only. If you naively try to run this policy on a completely different task, it will just not work because it was not trained for this reward function. Model-based, on the other hand, the pros is that it's easy to collect data in a scalable way. Indeed, when you have learned a good model of the environment, you don't need the simulation, or even you don't need the real world anymore to collect data. You can just put the model running on a lot of compute power. So in the case of a deep neural network, you just replicate it on a lot of GPUs, and then you can do really fast inference in a scalable way to collect a lot of data really, really quickly. And so that's why it's a really good idea. And also you can transfer the model across tasks because the model, remember, was only there to predict the transition function. So what happens when you take action A and are in state S. So it's all about the dynamics. It's not about what actually you want to do. It's just about what happens. So you reuse this model for the tasks that are in the same environment. And also because you incorporate more knowledge and you are trying to learn more things about the environment, there is less need of supervised data and it's more sample efficient. But on the other hand, there are some cons. You are just a model by itself does not optimize for task performance. And because of these reasons, it might be harder to learn than a policy. So, I mean, no, it's a different thing. A model of the environment, especially, for example, in the case of a complex physics in a 3D environment, might be really complex. Because you might need a lot to learn a lot of things. You might need to learn the visual effects of the environment. You might need to learn the physics of the environment, which might be very complex. But you can still imagine in this environment, for example, a task where the best policy just goes straight. And this policy is extremely simple. It's a constant policy. You output the same action, just go straight forward all the time. And by chance, this might be the best policy, even though the environment is extremely complex otherwise. And so in this case, the model is way more complicated. Also, sometimes you need assumptions to learn complex skills. This is more like an advanced stuff. But I would add also another concept that I didn't put here, but model-based is in general more complicated to implement because, of course, you have more parameters and you have more modules, you have more stuff to train. The algorithm is more complicated. And especially, it might be really hard to tune the hyperparameters to find the optimal one so that your training goes well. But sometimes that's the cost to pay for better sample efficiency and better performance. To summarize and finish on this last course, model-based is underexplored. So today it's a booming quite a lot, but still because of maybe the difficulty and still the limits that I explained, like error compounds and difficulty to learn models from random data, it's still underexplored and it's not, the potential is not completely achieved. Although now the idea of learning world models for everything is becoming quite popular in research. And there are a lot of active and exciting areas. So model-based approach with high dimensional observation, so from images. How can we do? How can we still do with the big images, so latent space stuff, as I explained. Other ideas are combining elements of model-based planning and model-free policies. So now the boundaries between the two are becoming more and more blurry because some algorithms take a bit of both. So technically, they are both model-free and model-based. And popular ideas that are very recent and on a personal note that is related to my PhD subject is representation learning and pre-training of models. So, for example, you might want to at first just learn a big model in the case of a complex environment that to pre-train on a lot of different tasks. And then, and once you have learned this model of the environment, you might use the model as to quickly learn a policy on a new task with, for example, fully model-free learning, but you might reuse the model to implement the policy in the early layers, for example. I did like that. That was a bit, intense, but also I think it's one of the most interesting areas now because the realm of possibilities is expanding every day, and there are every day new ideas in this field. So even though the algorithm, like simple that I showed you, is not the state of the art anymore, it's quite still close to what is being done today, and there are lots of exciting research right now in this area. And if you have any question, don't hesitate, of course. I didn't see anything in the chat. But okay, if so, the slides are on the Indino, of course. Okay, and if you have no question, then we will go to the second part of the class. And here, I mean, I'm probably gonna stay here, but also maybe if you want to talk to me about your project more just personally, you can just send me a message, and we can have a chat about if you are stuck on a research problem. Like I know doing some reinforcement learning problem is not the easiest project ever compared to deep learning. So that's why I want to dedicate this session also if you have some struggles, so that you can still show some interesting thing for the presentation next week. I hope that's all right for you. Is that is that clear? Can I have some feedback, maybe, or is that okay?
I have a question regarding
Yes.
to the slide.
Yes.
Wait.
Yes.
The version 2, the MPC method.
Yes.
Like from step 2 to step 5, I see there is no gradient descent regarding to the policy, like how we optimize the policy.
Yes, because in this case, we replaced, actually, yeah, I was not clear. Where is it? Version 2. Okay, version 2 is this one. Okay. Where you mean this slide, right?
Yeah, this slide, like I see it's like trying to pick the, it's trying to optimize the network F, but like after step 2, there is nothing related to the policy, like will it...
Okay, yes, you are right. Well, it's because in this case, so you can imagine that you are still learning some policy network, but also you see that in step 4, we introduced the controller and planning to help with the model error. And so there is no point if you have a controller to learn also the policy at the same time. But you're right. In this case, if you do model predictive control, you don't learn a policy network anymore.
Okay, so this one is just to try to train a better world model.
Yes. And there are just multiple ways of selecting the actions now. But yeah.
Okay. So when we select the actions, okay. Like when we select the best actions, you have like options like A, B, and C. For example, I choose the option C to choose an action leading to the best future, right? What if my action space is continuous? Like it's a continuous action space, then how I can choose the best actions out of this limitless action options?
Yeah, if your action space is continuous, you might have to implement a policy. You are right. That's the whole reason we introduced policy gradients. Yeah, if you have discrete actions, you might get away with just backpropagating and seeing what action gives the minimum error.
Okay.
But you are right. But if you have continuous actions, you might not be able to do that anymore. So either you use planning to choose the action, or you might have to learn a policy. But when I mean policy, a network that predicts an action. Yes, you are right.
Okay, thank you.
But this algorithm is it's more like because the not the problem, but the thing with model based is that there are many different ways of doing this, and this is just some examples of how model based might look like. And in this case, if you add some planning in it, but all the algorithm you will see in research look a little bit like that with some little differences. So as long as you understand that you have two ways of generating action, you either have planning or you learn a policy, and that you understand that you learn the model and you can use the model to learn the policy, or you do planning, that you understand what's important. But this algorithm is just like some variants, but there are many other variants where actually you might do things slightly differently. It was more like an example.
Okay, thank you.
No problem. Any other question? Well, okay. If there are still some questions after, don't hesitate, okay? And also, yeah.
Sorry, Tom, you mentioned that we can send you an email or drop the message to ask about the project.
Oh yeah, no, yeah. So
Okay.
yeah, exactly. So just maybe we can do a pause of like 15 minutes, or 10 minutes. But then yeah. So maybe I will not stay here, but yeah, I encourage you to send me a message on Teams right now, and I will go with you more like one-to-one, or like with your group to help you more specifically if you need. I think that's the best way to do it.
Okay, we will try to, but most probably we'll send an email just explaining.
Yeah, no, no, but the objective is that during this the next hour and a half, I'm available. So you send me a message on Teams, and we do a quick call with the group, and so I can help you directly with the problem, and we don't have to write by emails. But also, yeah, but if it's not urgent, you can also send an email for later. Okay.
Okay, thank you.
Okay, then yeah, I will leave the call, and if you but yeah, don't hesitate to send a message on Teams if you have questions about your project or need help, and I will start a video call with you, and we can figure out stuff together. Okay.